All right, good afternoon, everyone. I see that most persons are logged in, which means that the information that was provided has been received. So we'll come again to our system. This is our second lesson, and we'll just pick up from where we left off. So last time um, we were looking at the network and noting that there were various voltage levels that were included. Now, the fact that we have these varying voltage levels, one of the challenges, or the fact that we have different voltage levels, what that means is that we have a number of transformers in the network. Once you have a transformer, it means that you have to consider the turns ratio of the transformer. So the current on one side of the transformer will obviously be different from the current on the other side of the transformer. So if we're doing calculations, for example, on our single line diagram, based on what I'm showing here, for to do some calculations on this, then we'd have to always bear in mind that moving from one side of the transformer to the next, we are going to have issues with respect to the change in currents. So, it could not be just a simple analysis using the reactances as we have them. Now, to solve this problem, we use a system known as the per unit system. And per unit, well, we mentioned that this is what we just outlined, that the main purpose is that we have a system which the transformers, it helps to simplify the network. So if we put these voltages and currents and reactances in per unit, the benefit is highlighted in the second bullet point, which is that moving from one side of the transformer to the next, the per unit value remains the same. So if I'm looking at the impedance or the reactance to the transformer from the low voltage side, it will be the same per unit reactance going from the high voltage side. So that per unit reactance of the transformer will remain the same regardless of the direction I'm going. So it will not be until I have completed my analysis in per unit that I would then convert the values that we have found to the actual current and voltage values that exists in the system. All right. So just let me know when you have this. Okay. Finish with this? All right, so while per unit helps us in treating with the transformer, There are some other benefits that we can consider. These benefits include, one, when you think of certain types of electrical equipment within the power system, the per unit values lie within a rather small range. So, in other words, if you see, for example, a transformer with a per unit reactance of 0.8, right away, over time, with experience, you would know that that is a little off. Because usually the transformer reactance is somewhere in the region of about 0.1 to 0.2, 0.25, maybe up to 0.4, depending on the size and use of the transformer. So that small range that we have for these equipment, you can get a sense of whether or not it's correct. Similarly, for the reactance of a generator, the per unit reactance, would be maybe in the region of 0.2, 0.25, 0.3, 0.4. You see something like 1.1, then you immediately would pick up that there's that error. But as I said, this is something that would come with experience. And of course, the manufacturers usually specify the ratings of their equipment in per unit. And just to clarify, or not clarify, but highlight the fact that the per unit value that you get from the manufacturer is usually on the rating of the equipment. All right. So if you are told that the per unit reactance of a generator is 0.15, then it means that it is 0.15 on the rating of the generator. And we'll explain that, or you see the importance of that in a few minutes. So the key benefit is that with time, you will have a sense of the range of reactances or the per unit ratings of various pieces of equipment. And so you can quickly identify where errors are in the values that are presented. All right. So what is per unit? What really is per unit? Simply put, the per unit value of a quantity is calculated as the ratio of the actual, so the actual value of the quantity, to the base value of that quantity. So per unit, it's the actual divided by the base. So whatever the rating is, whatever the value is, that value, of course, the specific unit divided by the base value. So we can have per unit of voltage, power, you name it. All right. So per unit values. So based on this definition, per unit voltage would be the actual voltage divided by the base voltage. And we denote the base with the B. The per unit power. And yes, I'm using the apparent power here. Per unit power is equal to the actual power divided by the base, and it follows. Per unit current, the actual current over base, and similarly for the impedance. All right. So the actual quantity, so we talk about actual. The actual quantity is the value of the quantity in the actual unit. So if you're talking about voltage, it is the voltage in, and we use some standard values because we're talking about power systems. We usually specify the voltage in kilo, yeah? So it's the voltage in kilovolts. For S, it would be the power in MVA. Yes. If it's a small network we're dealing with, then we may use kVA. For the current, it's in kiloamps. And for your impedance, ohm. So actual refers to the quantity in the value, is the value of the quantity in the actual units. And the base quantity is also in the same units, which therefore makes the per unit value dimensionless. And sometimes instead of the per unit, we use the percentage value. And the percentage value is simply calculated by multiplying the per unit by 100. So if you have a per unit of 0.1, then the percent value is 10%. All right. Now, in per unit, we have been talking about base values. What are these? For any system that you're going to use per unit calculations, for any system, there are two base values that are selected. And I know it is written in white here, so I'll just circle for emphasis. These two values are arbitrarily selected. There is no rule in terms of how we select them. However, although they are arbitrarily selected, there has to be some, for use of a better word, some common sense applied. All right? And so usually persons select base values that provides easy division. So in for the power, you may want to select 100 MVA. Yes. For the voltage, you would select a multiple of one of the system voltages. Yes. So since we're dealing with at the transmission level, and if we're looking at let's say a Jamaican network, then we make select 69 kV as the base. And for the voltage, it is selected at a particular point in the circuit. All right. So the base kV, the base voltage, is selected at a particular point. Now here we highlight that the base values, it's either the three phase, which is a line to line, or the phase, which is a line to neutral voltage. Yes? And the three phase or single phase apparent power. So if you are going to be working with the three phase, or if you're going to be working with the line to line voltage, it means that you'll be working with the three phase power. If you're going to work with the phase voltage or line to neutral voltage, it means that you'll be working with the single phase apparent power. It really doesn't matter because whichever one you choose, the per unit value would come out to be the same. So whether you choose the phase, single phase, or the three phase values, you will always end up with the same per unit value. All right? So in terms of the selection, as I said, arbitrarily selected. And I also mentioned before that because we're dealing with a power system, the base voltage is usually in kilovolts. And the base MVA usually, or the base power, base apparent power is usually megavolt amperes. And once you use kilovolt and megavolt amperes, then your current base, which should now be a derived quantity, your current base would be in kiloamperes. All right? Because you'll have the kilo times kilo to give you the mega. And for your impedance, that would now be in ohms, because you're dealing with kilovolts and kiloamps, so you get ohms. So these are the standard values that we would use. But the key here is that the base voltage is in kV, the base power is in MVA. And if you wish to note it, you can take that. The units that we are using here, the kV and the MVA, is just because we're working with a power system. All right? But if you so desire and want to use volts and volt amperes, be my guest. It will only require another page or two. So just to provide greater clarity to the previous slide, yes, where we said that the base values can either be the three phase or the single phase. All right, just to provide some clarity to that. All right, so take this one. So we have base values. For the apparent power is 30 MVA, and for the system voltage, it is 120 kilovolts. Is everybody with me? Have I lost anybody so far? Am I going too slow? Am I going too fast?
No, sir. You're at an okay pace.
All right, good. All right, so here's our system. So the three phase power, 30 MVA, and the line-to-line voltage, 120 kV. Now, if the actual, let us say the actual voltage is 108 kilovolts, and the actual power is 18 megawatts. And don't be too concerned about the fact that I'm using megawatts here. I'll explain that in a few minutes. The per unit values that we would have for these two, per unit voltage, remember we said per unit is actual over base. So the base voltage here is 120. So the per unit voltage would be 108 over 120, which gives us 0.9. And the per unit power would be 18 over 30, which gives us 0.6. Fair enough?
Yes, sir.
Now, I have done these calculations using the three phase values, the line-to-line voltage and the three phase power. Now, if I were to convert these three phase to single phase values, for the voltage, we'd have the base voltage over root 3, Yes? And for the power, it will be 30 over 3. So the single phase values, yes, the single phase values, VB would be equal to 120 over root 3, which is 69.2. And SBS would be 30 over 3, which is 10. All right? If I found the actual values, because remember the values that I give, the actual values that I gave earlier would have been the three phase values also, yeah? So the single phase actual values, I mean, you know, the single phase actual values would have been 108 over root 3 and 18 over 3. So you get 62.3 and 678, 62.3 kilovolts and 6. All right. So if I were to therefore find the per unit voltage, all right.
Sir. Go back a bit, sir.
Do you mind going over the actual phase value again, please?
The line to line actual was 108. So therefore the phase would be 108 over root 3. Yes? No?
Yes, sir.
All right. And for S, the actual was 18. So obviously we're assuming here that we're dealing with a balance system, all right? So S would be 18 over 3, which would give us 6. So if I were to one step, somebody was saying something just now?
Yes, sir. I was saying, why for S you have 3 instead of root 3, sir?
How do we find, if I have the power per phase, how do I find the total power?
If you have the power per phase, I said. Oh, you times it. You times it by 3.
Yeah, man.
Okay, sir.
All right, cool.
Question, sir.
Uh-huh.
Does it differ when dealing with does it differ when dealing with a star system and a delta system?
The assumption here is that it is a star system with a neutral point. If it was a delta, then V line and V phase would be the same, no? Isn't that the case?
Yes, sir.
Yeah. All right. So that's the assumption here. That's the assumption here. I should have said that. Thanks for that point. All right. So if I therefore calculate the per unit again, all right, then from the actual values, the corresponding per unit would be the actual per unit over the base per unit, which gives me back the 0.9. Yeah. And of course, the actual over the new base, which gives me back the 0.6. So the point that we're making here is that whether you use the three-phase value or the single-phase value, the per unit value will come out to the same thing. That's the key. That's the takeaway that you need to work with. For the most part, during the calculations that you're going to be doing, we usually just take the three-phase value. But the point is, it doesn't really matter. Per unit remains the same, and that is the key. All right. So earlier, I made mention of the fact that you must not be bothered by the fact that I was saying that the actual power was 18 megawatts, even though I said that the base MVA, the base power, was in MVA. No, the reason that that is not an issue is because for the per unit system to be valid, the following must be true. All right? The validity of the per unit system is based on one, that P base is equal to Q base is equal to S base. So in other words, whatever value you use for the apparent power, the base MVA, that must be the same value that is used for the active and the reactive power. Of course, we know that S is equal to P plus JB. So, that would follow. So S base is equal to P base is equal to Q base. But bear in mind, what you will select, yes, what you will select would be S base. Nothing else. You select S base. And S base would be the same value that you use for P and Q. All right? We can then derive, once we have selected the S base and the V base, we can derive I. So I base would be S base over root 3 V base. All right? Okay, folks. Now, we select S, we select V, we can find I. The other point we need to make is that, again, for the per unit system to be valid, yes, Z base must be equal to R base must be equal to X base. Again, Z equal R plus J, so it means that the base would be the same. All right, for that equation, for either side to remain balanced, it means that we'll be dividing each side by the same quantity. Agreed? Because we wouldn't have changed anything. You would have the same phase angle if you divide each of them by the same base. So Z base must be equal to R base must be equal to X base. Of course, Z base is a derived quantity, right? So Z base is equal to V base squared over S base, or if you want to use V base over I base. So we're just setting the ground rules before we get into some problems so that we can, get a better understanding, a better feel of this whole per unit thing. I mean, on the surface, it's quite simple. It's quite simple, but you have to think about it. It can become a little tricky. So we want to ensure that we understand the fundamentals. All right. Now, similar to Z base being equal to R being equal to X, the same must be true for the admittance. So Y is equal to B is equal to G. So your admittance base, which again is calculated, and that admittance base will be equal to the reciprocal of the impedance base. Okay? So, what are the relationships that we have established? We have said that S base equal P base equal Q base. I base can be calculated or derived having selected S and V. Z base is equal to R base is equal to X base. Y is equal to B is equal to G, which is equal to 1 over Z. Now, these relationships, we also have some conventions. And these conventions, you have to take very careful note. All right? So the conventions, are you ready? Convention number 1. S base is the same for the entire power system under consideration. So if I'm looking at the Jamaican network with all the bus bars considered, the system base would be a single value. That system base may be 100 MVA. So it means that every piece of equipment would be referred to that 100 MVA. So when you look at a piece of equipment on system base of 0.1, yeah, it means that with respect to the system base of 100 MVA, I said earlier that manufacturers would give the per unit value based on rating. I know I'm maybe going ahead a bit, but the manufacturer, for example, let us say we have a 25 MVA transformer with a per unit reactance of 0.28 on rating. That transformer, when I buy it from the manufacturer and I decide to use it if I use it in the Jamaican network, if the network has a system base of 100, I would then have to convert the reactance that the manufacturer gives me, which is the 0.28. I would now have to consider it, know that it is part of a 100 MVA system. So the 0.28 only refers to the rating of the transformer, which is 25 MVA. But when I move and use it in a system which has a base of 100, I now have to update that reactance value. I will talk about that in a few minutes. So the first convention is that the system base, S base, is used for the entire system that we are considering. Convention number 2. Convention number 2. is that the ratio of the voltage bases on either side of the transformer, yes, is selected to be the same as the ratio of the transformer voltage ratings. So in other words, remember, what rule is there? Anybody, what rule is there? Or what rule do we apply in selecting the base voltage? What's the rule?
Sir, it has to be easy to work with, sir.
That's not really a rule. That's a nice to have. What's the rule?
So divisible by the nominal.
Huh?
So it's divisible by the nominal voltage, sir, or a multiple of the nominal voltage.
Actually, I'm being very disgusting right now. The rule is that there is no rule. It's arbitrary. It's arbitrarily selected. You are going to select one that is in your best interest. You with me? But it's arbitrary. So if it is arbitrary, if I therefore make an arbitrary selection, and remember I said that you select it at a point. Remember that? So you're gonna select it at a point in the network. So if you make the arbitrary selection of VB1, so let us say, let us say it is, we select that as 100. All right, so VB1 is selected as 100. And the turns ratio of the transformer, on the side that we selected VB1, let us say the voltage there is 300 volts. Yes? And let's say on the other side, it is 900 volts. Okay? So if I selected VB, remember this is arbitrary, VB1 is selected as 100, it means that 100 over X, because I'm now trying to find what VB2 needs to be. We already know the turns ratio of the transformer is V1 over V2, which is 300 over 9. Agreed? So it means that X in this case must be 300, because 100 over 300, it must be in the same ratio, or should I say 100 over X must be in the same ratio as 300 over 900. You with me? Is that clear?
Yes, sir, it is.
Yes, sir.
All right,
Yes,
cool.
sir.
So let's get back to this now. All right. So to give you an opportunity to put your, try your hand at this, take this question from it, please. All right, do we have this? All right, so
Yes, sir.
the silence means yes.
Yes, sir.
Yeah, man.
So let's make sure we understand it. So we have a two-phase, a two-winding transformer rated at 150 kVA. We have the turns ratio, yes, 13.8, 2.3 kV. And the equivalent leakage reactance is referred to the 2.3 kV winding is 0.12 at that phase angle, right? And we're going to use the ratings of the transformer as base value. So we're not changing any base. We're using the ratings that we have here. So it means that on the high voltage side, the base value would be 13.8, and on the low voltage side, it will be 2.3. The 0.2, when we say refer to the low voltage side, think of it as when I look into the transformer from the low voltage side, the reactance that I am seeing, or if I was to measure the reactance, it will be 2.3, it will be 0.12 ohms, right? So I hope everybody understands the question before us. So in terms of the solution, yes, in terms of the solution, based on the ratings that we have, yes, the base impedance would be VB squared over SB. All right? And remember, we are using the base values. So on the low voltage side, the base value is 35.267. So if I have the base and I have the reactance looking in, I can find the per unit. So if I look at the transformer from the 2.3 kV side, the per unit reactance would therefore be equal to 0.12 over 35.267, and that will give me 0.0034.
So go with that again, sir.
All right. Do you understand what the question was asking or was saying? In terms of the 0.12 being referred to the low voltage winding. Do you understand what that means? That the leakage reactance from that side is equal to that.
Yes, sir.
Oversimplifying it, if I was to measure the reactance from that side, I would say 0.12 ohms. But we all know that because we're dealing with a transformer, when I look at the reactance from the other side, the value is going to change by a function of the square of the turns ratio. All right? Which you would have already done in machines, right? That's all like machines 2. All right. So if I now go to winding 1, which is the high voltage winding, but I think you asked me to go over this. So all I did was to look at the reactance. Well, let me come back. We're looking now at the base voltage, base impedance, sorry. The base impedance is voltage over S, voltage squared over S, which is the 2300 or 2.3 K squared over S, which is the 150 kVA. All right? So we get that in ohms. Fair enough?
Yes,
Which
sir.
means that the per unit is the actual. The actual is this, because this is what we are seeing from that winding. So that is the actual. So the actual divided by the base, and we just calculated the base impedance. Remember we said earlier, once you have S and V, you can derive I base and Z base. We said that earlier, right?
Yes,
There's only
sir.
2 quantities you are going to specify, S and V. All right? So we can now calculate our per unit. All right, so now I go to the other side of the transformer. And first I need to know what the leakage reactance would be looking from the high voltage side. So Z1 from the high voltage side.
Sir,
Yes.
can I go back for 5 seconds and finish right at the last line, please?
Should I start counting now?
Yes, sir, you can go. Good now,
All right.
sir.
So on winding 1, which is the high voltage winding, Z1 is equal to N1 over N2 all squared times Z2. All right. So that gives me 4.32. All right. So this now is the actual value on the high voltage side. Now, the last note we made, remember the conventions that we spoke about? We said that the ratio of the base voltages must be the same as the turns ratio of the transformer. So the base voltage,
Yes, sir.
the base voltage on the 13.8 kV side will also be 13.8. So it means that ZB on the high voltage side will be 13.8 all squared over S. And that gives me 1,269.6. And if I now calculate the per unit value looking from the high voltage side, I get the actual. Remember, that's the actual because we had to deal with the turns ratio divided by the base, and we see that we get the same per unit value, which, ladies and gentlemen, is the purpose of per unit. The purpose is that the per unit value going across the transformer remains the same. So if I have my one-line diagram, I can now just add the reactances if they are connected in series, even when I'm crossing a transformer, because regardless of which direction I'm going, where the transformer is concerned, the per unit reactance remains the same. So Z1 per unit equals Z2 per unit. Okay. Any questions? All right. Go then. So here we have an ideal single phase transformer. We have the per unit voltage the primary and the per unit voltage, and the secondary also the per unit currents on either side. All right. And what we are seeking to do here is to find a relationship. I mean, we have already stated it, but we just want to show the relationship between the per unit voltages. All right. We know that this is true, that the turns ratio will be equal to the voltage ratio. Yes? So E1, let's just transfer in E1 equal to N1 over N2 times E2. And if we choose the base on winding 1, base voltage on winding 1, V base, if we divide throughout by that, right? Whatever E1 is equal to, we now divide that by VB1. Yes, dividing that by VB1, we would get E1 per unit. Because remember, per unit is actual over the base. Were you comfortable with that?
Yes, sir.
Yes, sir.
However, we have already stated that this is true. VB1 over VB2 is equal to V1 over V2 or equal N1 over N2. So E1 per unit, N1 over N2, E2 times E2 over VB1. So I'm going to substitute for VB1 in this equation. We're going to substitute for VB1, yes, in terms of N1 and N2 and VB2. So from here, from this, all right, I'm going to substitute, make the substitution. All right, so all of this would have been VB1. So by doing that, we see that the N1 over N2 would cancel. So this will cancel this. And what I'm left with is E2 over VB2. E2 would be the actual voltage on the secondary side. And if we are dividing the actual voltage by the base, we're going to get per unit. So in other words, we are saying that the per unit voltage on one side of your transformer will be equal to the per unit voltage on the other. So we're just proving that. And we're saying that we can do that also for the current. Where are we? 4 o'clock. Okay, we're doing good time. Okay. Now, earlier, I made mention of the fact that, when you bring a piece of equipment into a power system, that you'll have to change the per unit value, because the per unit that you get for the piece of equipment will be based on the rating of the equipment. So you'll hear reference being made to per unit on rating or per unit on system base. All right. So the per unit on rating is what the manufacturer will give to you. The per unit on system base is when you have now connected that equipment, that piece of equipment, to the network. You have to change that per unit value when you are going to do your calculations. All right? And to do that, we talk about change of base. How do we go about changing the base of a piece of equipment? When you buy it, the base value, since I'm giving the value on rating, it means that the base value would have been the rating of the equipment. But when I bring it into the system, the new base value is the system base. All right? So all that I just said is nicely written for you. So how do we go about doing this? All right, so again, I go back to the fundamental principle, which is that per unit is equal to actual over base. All right? Now, regardless of what the specified per unit value of the equipment is, again, regardless of the value, the specified value, per unit value of the equipment is, that per unit is based on a particular base value. However, the actual value, actual impedance or reactance of the equipment does not change. So when I make a transformer, if the reactance of the transformer is 5 ohms, and I put it in a system where the impedance base is 20 ohms, it means that the per unit would now be 0.25. All right? If I take out that same transformer and I put it in a system where where the base value is 100, it still has 5 ohms. But because the base is now 100, it means that the per unit reactance will now fall to 0.05. Are you with me? So the actual value, it can't change. I mean, if I take up the transformer from Jamaica and carry it to Mexico, it's the same transformer. It's the same 5 ohms. But when I put it in a different system with a different base, the per unit value will change. All right. So on that basis, the new per unit will be equal to Z actual over whatever the new base impedance is. We understand that? But the actual would be equal to the per unit times the old base. Nothing fancy about that. So I just make the substitution for the actual impedance, which is ZPO, PU old, times Z base old over Z base new. And remember, what I'm interested in finding is the new impedance, because I'm going to put it into a system with a new base. So I want to find the new per unit impedance. That's my focus. So I'm not going to change that. So what I'm going to be playing with is this. But we have already determined how we go about finding base impedance. We know that impedance kV squared or base voltage squared over S base. We already know that. So we can make the substitution.
Sir,
Yes.
based on the quantities that are given oftentimes, we could use the base voltage and the base apparent power to find that same new impedance per unit.
Before we what we are looking at, what we are trying to do is that we want to determine what this is. Remember what I said, this does not change. So the actual impedance does not change. All right? You have to keep this in the back of your mind. This doesn't change. As I said with the transformer, it is 5 ohms if I'm using it in Mexico. It is 5 ohms if I take it to America. It is 5 ohms if I take it to Jamaica. What will change is the per unit reactance or impedance, because the impedance base of these systems may be different. So the actual doesn't change. So what we are trying to find is an expression for the actual impedance. And the first one we did was to say, based on where we're coming from. Remember the base, the Z base, the old Z base would be on rating. Because remember the actual impedance, the per unit impedance that you would have gotten. Remember when we started out, I'm backtracking now all the way to the start of the lesson. We said that one of the benefits of per unit is that this is how manufacturers specify the rating of their equipment. Remember we said that? Hello? Remember we said that?
Yes, sir.
Good. So when the manufacturer tells you that the per unit is 0.0 One, what he's saying to you, what he's giving you, yes, is this ZPU old. But that ZPU old is given based on this Z base old. So when I multiply them, I will get the actual impedance. Because remember, per unit is just actual over base. So I cross multiply, so I get actual. So I've now made the substitution here. So to go to your question now, what I want, remember this is what we're after, yes? I want an expression for the base values. And I know that the base values, the base impedance, is a derived quantity, which is based on the voltage and the apparent power. So I'm going to make that substitution. So I'm going to find the base values now. So just watch carefully. Go look in the notes. I hope you wrote it. You have an expression there for Z base. It should look something like KV base over S base, KV base squared over S base. Something like that. You have that now?
Yes, sir. Yeah.
Good. So we have already given you that. So for the
Yes, sir. That one was what I was asking about.
so Z base old would be equal to V base old all squared over S base old. And Z base new would be equal to V base new squared over S base new. All right? I think I jumped a step here, but it's all right. Huh? And then we are making the substitutions in the equation we had before for Z base old and Z base new. We are dividing them. So you have the V base old squared, yes, over S base. And because you're dividing that by Z base new, then the S base comes in the numerator and the V base new in the denominator. All right? Whoops. So for me, changing base, Z new would be Z old times, and if you want to, well, just write V base old first, and you know everything else falls in line. So we square that times S new over S old. So you know that V base old is the first one. Everything else falls in line. All right? So, Mr. Andrew, this is what you say you were asking. So we're good now.
Yes, sir. I'm okay now.
Cool. Oh, time flies when we're having fun. Okay. Just some additional bits of information. ZPU, is equal to Z, which is the actual over Z base, all right? No, some summary formula from what we had done earlier. Um, Another bit of information. This SCL here means a short circuit level. And the short circuit level is usually the maximum MVA to which a bus bar can be exposed. All right? I've had it there because it was a consideration, and I don't think I have asked you to look at it in Power World, but certainly it is something that I would have explored if you were looking at ERACs. Okay. So from what we had here, yes, ZPU1 was Z times S base 1 over V1 squared, and ZPU2 So what I'm giving here is just a general formula. It's not much of a change from what we just did. All right. We'll finish with this. All right. All right. So this is your general formula, all right, in terms of changing your base. I believe it or not, there is nothing further for me to say to you in terms of theory or per unit. But of course, we have to make sure that we understand what we just did. All right? So there's an example in your textbook, but we're gonna go through it here. All right, and here it is. Question is to draw the single line diagram for the network shown. And why not just find the per unit current flowing? That should be interesting. Okay, do we have this?
Yes, sir.
Yes, sir.
Okay. All right. So the first thing we need to do is to decide what MVA, what base MVA we want for the system. Because as we said before, the MVA base must be the same right across the network. All right. So we can choose an MVA. And we think, you know, what value you want to choose, it really doesn't matter. You just choose an MVA value. And then tell me why you're going to choose that, or why you have chosen that one. You all can answer at the same time.
Excuse me, sir.
I say you can answer at the same time, so I want to know which base value you want to choose. What base MVA?
Sir,
Choose here. Huh?
sir, 30.
Okay, why would you choose 30?
Sir, mostly because it has the highest value in the system. So it would help to reduce the amount of calculations you have to do.
So the latter part of what you said, I accept. It reduces the amount of calculation, but not because it's the highest, just that it is one of the values for your transformer. All right, so you have the 30 MVA here, 30 kVA. Fair enough?
Yes, sir.
And therefore, you would not have to do any conversion in terms of reactance based on MVA for that transformer.
Okay, sir. So not because it's the highest, just because it would not change the per unit of the transformer.
Yeah. And it reduces the amount of calculations that you have to do. All right?
Okay, sir.
All right. So the system base, we're going to take as 30 MVA. 30 kVA, sorry. The next thing we want to determine
Yes, sir.
is, yes.
Based on the explanation given for why he shows the 30 kVA, I was wondering if it would be the same if we chose 20 kVA.
Yeah.
Okay.
Absolutely. I mean, we could easily have chosen 100, you know. All right? But you would have chosen a value that, in this instance, would make your calculations, you have less calculations. Or you have less conversions based on S. And that's key, based on S. All right? All right, so there's a single phase system, and we want to draw the single line diagram for the system and calculate the per unit current in the load. All right? So that's our objective. So we have chosen the 30 kVA as our base. What else do we need to choose? Come on, folks. What else do we need to choose?
30 kV volume. Base voltage.
What the base voltage? And how do we choose that base voltage? What did we say about the selection of the base voltage?
Can be arbitrary.
It is arbitrary, but what else did we say? We said that it is selected at a point in the network.
Yes, sir.
All right. So we are going to select 240 volts at the primary winding of transformer 1. So we are going to let the kV base of 240, or the base voltage, so we're not doing the kV here. So the base voltage of 240 volts, 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 240 vol on the primary side of the transformer. So that's important. Okay, so the first thing we want to do is to calculate the per unit voltage for our generator. So what would be the per unit voltage for the generator? Huh?
220.
Per unit voltage.
Sir, the 220 over the 240.
2 over.
All right, so 220 over 240. So the first thing we're going to look at is for the generator. For the generator,
0.917
is equal to 220 over 240, which gives us 0.9167. All right. All right. Now, for the transformer, for transformer T1, what is the per unit value? Per unit reactance.
0.10.
All right, so XPU for T1 is 0.10 EU. Everybody comfortable with that? Is there anybody who unsure where we get that from?
No, sir.
All right, cool. So now, for the transmission line, what do we have for the transmission line? What do we have for the transmission line?
I think 2 ohms.
What does that
The
represent?
reactance.
So we have the reactance for the line. All right. So what do I need for that, for the line?
Need the per unit value.
I need a per unit value. So for the line, Z line is equal to 2 ohms. Now what is the base impedance on the line? What do I need in order to find the base impedance?
Sir, voltage squared base over the apparent power.
So we need V base squared over S base. All right. Now, what is the base voltage on the line?
Sir, would it be the 240?
480, sir.
All right. Why is it 480? Why is it 480?
Sir, is that side of the transformer is feeding the transmission line.
No, but yeah, but what did I give you earlier for you to know that it has to be 480? What did we say earlier that would prove that it is 480?
Sir, the selected base. selected base for the
What do you mean by
voltage.
the selected base?
The fact that we are using 240 volts.
Sir, is it because it is selected at a point?
You're very low.
Is it because it is selected at a point?
No. Earlier I said to you that VB1 over VB2 must be equal to what? V1
Turns ratio.
over V2. Yes? So based on what Mr. Ellis just said, what is VB1?
240.
240. So 240 over X. X is what we want to find.
Yeah.
What is V1?
220.
No, man. For the transformer we're dealing with them.
Oh,
What's
yeah.
V1? 240.
240, yeah.
And what is V2?
480.
480. So it means that X will be 480. So this one is simple, right? But that's what it would work out to. Okay? So V base, Z base for the line would therefore be equal to 240 squared divided by what's S base? What's S base?
30K.
30K. So 30K. And what's that equal to? I don't have a calculator, so I'm depending on you. What does that work out to?
Wouldn't it be 480 square?
What did I say? My God.
1.92.
No. My mistake. I am saying 480 and I'm writing
Okay.
240. So it's
240.
480,
Okay.
sorry.
I'm asking.
480 squared. 480 squared. My apology.
All right,
What is that?
7.68 ohms.
0.68.
So 7.68 ohms. Okay? So that now would be the base for the line. So what is Z per unit? For the line, what is Z per unit?
Is it actually
0.26.
0.26, sir.
0.26. All right.
Yes, sir.
No, we're only having some decimals there.
Oh, it's 0.
0.260.
260.
All right. I think I can have result to my phone to check that one. Folks, anyway, you will understand when you're dealing, especially with power systems, and that is why I try to drive it into your minds from networks. You don't just eat decimal places in power systems, because you're dealing with mega and kilo and giga, right? When you take off decimal places like this, you're taking off hundreds. Are you with me?
Yes,
Is
sir.
that clear? Word
Yes,
to the
sir.
wise is sufficient. I will not repeat myself.
Yes, sir. Yes, sir.
Yeah, man, we cool. All right, so we now have the line. So we have for the generator, we have for the transformer, and we have for the line. The next item we have is the transformer. And the transformer 2 is on a 20 kVA base. Yes? And the base voltage on that side is what? It's 480. Yes?
480.
Yes, sir.
Yes, sir.
All right. So what's the new base voltage? For this transformer, what will be the new base voltage?
460, sir.
Listen carefully.
120, sir.
No. Don't guess. The transformer. What's the turns ratio of the transformer? What's the voltage ratio of this transformer?
4480.
Huh? Look at the transformer, man. What do you have? Or you didn't write it down?
So this is
Go
for
back to-
transformer 2?
Sir, it's
This is the transformer
461.15.
461.
461.15. That's the voltage ratio of the transformer. Are you with me? No.
Yes, sir.
That transformer is a 20 kVA transformer.
Mhm.
But I am taking it and I am putting it in this network. This network on the 460 side, what is the base voltage on the 460 side?
240, sir.
For the net, no, don't guess. For the network, what is the base voltage on the 460 volt side of the transformer? The base voltage.
120.
All right. Think about this, Jen.
40.
Sir,
What was the base voltage on the line?
480.
So, would you have a line with voltages being different? Well, apart from, voltage drops. Would you have a line with voltages being different at either end?
No, sir.
No.
Huh?
No,
No.
sir.
So if the base voltage on the line on the 480 side of T1 is 480, what must be the base voltage on the other side?
120.
480 as well, sir.
480
480.
is a line. So the
Yes, sir.
voltage on either side must be the same. Apart, as I said, ignoring voltage drops that would occur, which is a normal part of the operation, yes? On the other side of the line, it will also be 480. So at transformer 2, so just to ensure that we get this clear, everybody have what's on this slide? Kind of coming back to it. Does everybody have what's on this slide?
Yes, sir.
All right, cool. So I clear that. So we can say on the line side, of T2, yes, Z base is equal to 480 volts. All right. Now, I know you just get the notes. I haven't gone through it as yet. So I'm not being hard on you. But I'm going through this because I want you to understand that although this thing seems simple, you have to think carefully. All right?
So should we do this?
No. All right, foolishness. No. All right, thank you. All right, no. It's 480 volts on the line side of T2. All right? It means, therefore, that the transformer would now have to operate, or the reactance of the transformer needs to be specified in terms of the new base voltage to which it is exposed. Are you with me? So what is the reactance of the transformer? What's the reactance of the transformer?
Per unit, sir?
One.
T2, T2. What is it now? 0.1. So Z is equal to 0.10 PU. Now this per unit value, what is it based on?
Based on the
Yeah. The manufacturer.
What is it based on?
Manufacturer.
Yes, the manufacturer data. And what is it based on? Come talk to me now.
So the system,
Huh?
based on the system.
It can be based on the system.
460.
Pardon me?
Based on the base voltage of the transformer.
No, it is based on the rating of the transformer. Remember we said that? That the manufacturer gives the per unit on rating. What's the rating of the transformer?
460, 150.
Again?
20.
460, 115 at 20
kVA.
kVA. So that is what this is based on. But because we are now putting it into a system, and what is the base MVA for the system? What's the base MVA for the system?
20 kV.
30. You told me 30. It's 30. So what we want, therefore, is Z new. So we want it on the 30 kVA system. All right? So Z new is equal to Z old. And I said you start with what? V old. What is V old? What is the voltage of the transformer on that side?
30, sir.
V.
V.
What is V old? On the line side of the transformer. What is the voltage on the transformer?
480, sir.
460.
460. Okay. And what is the, because 460 would be the old base, you know. What's the new base? What are we converting it to?
480, sir.
Yeah,
480. Thank you. Squared times, what's the new S base?
30 kVA.
30K over, what's the old one?
20 kVA.
Work that out now. So 460 over 480, all squared. Times 30 over 20.
$0.13776.
Again?
0.13776.
0.137. So that now is the new per unit value for the transformer. All right. So on rating, what the manufacturer gave you was 0.1 for this 20 kVA transformer with a turns ratio of 460 to 115. However, you are now putting it into a system where the base voltage at the point you connect the 460 is 480. And the base MVA for the entire system is 30. So you now have to change base. because the rating you got, the per unit rate value you got, was based on the rating, which is what was made. It was made with. Are we clear?
Yes, sir.
All right. So what we are doing is applying everything that we have gone through since 3 o'clock. And then finally we come to the load. Obviously, load is an impedance. Eh? Now the load is connected to the 115 voltage winding of the transformer. Yes? But what would be the base voltage at that point? Everybody have what is on the slide?
Yes, sir.
So I can erase this.
Yes, sir.
So on the load side, of the transformer, yes, V is equal to 115. All right. However, remember what we said, that the base voltage or the ratio of the base voltages must be the same as the turns ratio. So we know that for the transformer, the turns ratio is 460 to 115. Agree?
Yes, sir.
The base voltage on the line side of the transformer, we just showed that to be 480.
480.
So we want to find what the base voltage on the load
VB.
side would be equal. All right? So you cross multiply and you get VB to be equal to 480 times 115 over 460. All right? What do you get? 120?
120.
You get 120 volts. So the base voltage on the load side is 120. So you now can calculate Z base on the load side. Z base would be equal to V base squared over S base. Yes? So it would be 120 squared over 30K. All right, what does that give you? Pardon?
0.48.
0.48. So if that is the base voltage, then for the load, ZPU would be the actual. And what's the actual for the load?
0.9 plus J 0.2.
Are you dividing that by the base, which is Z 0.48? All right. How are you again?
One point at the angle at 12.529.
No, give me rectangular. Give me rectangular.
Okay.
Sir,
153.
Go again?
153.
Oh, that can't be correct. 0.9 divided by 0.4, it is 2 times 9, that's
0.1 per
18.
unit plus J 0.2.
Go again?
0.1 per unit.
75, sir.
1.875. Yes.
1.875.
Plus 0.4166.
4166. Yeah, that sounds like it. Come, folks, just look at what you're dividing here. Yes? This is almost 0.5, right? So 0.9 divided by 0.5 would be 18. 0.2 divided by 0.5 would be 0.4. So, you need to just look at what you're dividing and know if you're off. All right? So we have now found the per unit for all the equipment in the network. But the objective was to find the single line diagram, right? To draw the single line diagram, or the reactance diagram, sorry. Yes? And then we can calculate the current. All right? So let's see how we go about that. Do you have everything that is on the slide?
Yes,
I'm
sir.
going to erase it.
Yes, sir.
All right, good. All right, so now I'm drawing the reactance diagram. So I start with the generator. And next I have the transformer. Then we have the transmission line. And then we have the transformer. And then we have our load. Okay. And that's my circuit. So we have reduced that power network to a simple reactance, or well, I should say impedance, since we have R and L for the load. All right. So for the transformer, it is X, right? So since it's X, it is then J0.1. Okay, J0.1. For the line, we have J0.2604. Okay. For the next transformer, it is 0.1378. 1, 3, I think you said 776, right? I think that's what we had there.
Yes, sir.
Good. And then around here, we have 1.875. All right. And up here we have J 0.4167. All right. And then for the source, we had 0.91666 recurrent, right? 67. That time is here. All right. So that's my reactance diagram. And the per unit current would be equal to 0.9167 divided by ZT. So you can just add up all of these. And this is the beauty of per unit, because although we have a transformer there and a transformer here, I can still just add them, because whether I am going in this direction or that direction across the transformer, I will see the same per unit value. All right. And once I have found the per unit current, the same per unit current will be flowing throughout. All right, the same per unit current will be flowing through. However, the base current will be different depending on the section of the network that you're working in. Yes, because over here, that's section 3. Let's call that section 3. Yes, the base current would be 30 over 120 because the base voltage over there is 120. Agreed? For the section up to the transformer, I should really put it in the middle of the transformer. All right. So scratch this. It's up to the middle of the transformer because on either side of the transformer, it will change. Agreed? In this section, let's call it section 2, the base current will be 30 over 480. Okay? And over here, the base current would be 30 over, what was it, 240? Over 240. All right? So whilst you have the same per unit current flowing through the circuit, yes? Based on these base current values, all right? You would get a certain current value, actual current value over here, section 3. You get a different current value there. Bear in mind, you have a transformer, yes? So the transformer would cause the current through the line to be different. But when it comes out the other side of the transformer, that will be sector 3. And then in section 1, that base current will be 30 over 240. So you'll get a different current here. And yeah, that's it for per unit. Save and accept, you know. A lot of people, well, I didn't expect everybody to be shouting the answers. But I am not convinced that many persons are up to scratch with the test. Yeah, so there are 2 questions. If you have a class, then fine. If not, I'm going to put up the 2 questions and you write them off now. All right? Wow. We're bang on 5 o'clock. So that is it from me. If you have no questions, do you want anything clarified here? Yes, no?
Sir, all the things that we have found, they're all impedances, correct? Just for clarification. Like the transformers and the line, we have all found them in terms of impedance.
What we did was to use the values that we selected in terms of the base MV and base voltage to find the base impedance.
Okay, sir.
And what we calculated were actually reactances. There's only one impedance that we calculated, which was for the load. The others were reactances.
Okay, all right, sir.
Good. So, with that said, here's question number 1. Oh, that's not. So take this one. All right, so in the interest of time, what I'm going to do is just to pan to the next, to the rest of the question, and you can go to YouTube later on and, you know, take the information, all right? So it will be at the end of the lecture. So the question, these are the This is the information that is with that question. And then the second question, all right? And here's the circuit. Okay, so it is no part of the recording. So you can go to YouTube and get that. What am I asking you to do with this? Just to make sure that everybody does some work and make an effort to understand what is being done. Today's what? Tuesday? I say I'll give you until Friday, all of 3 days, to do these 2 questions, and you will have a link for you to upload them. All right? Please, do your own work. From time to time, I may just decide to do a little oral just to make sure that you actually did the work. All right? But
Okay,
let us not have to go to that level. I mean, we're at level 4 now, and I kind of stopped doing that type of thing.
All right.
All right? So have a good rest of the afternoon into the evening.
Dr. Isaacs?
Yes.
Hi, sir. Just wondering, the class that is scheduled for tomorrow evening?
There's no class scheduled for tomorrow. It's a lab.
Okay, sir. Okay. All right, noted.
All right. So
we'll be addressing the lab matters, right?
Huh?
In that session tomorrow evening, sir, we are just.
Yeah, man. If you have an issue, what I will do, as I said, did I say that? I'm almost sure I did. No, it's not you. I will set up a discussion forum. So I will open a lab forum. If you have issues with the labs, then you put it in the forum, and then we make a decision whether or not we need to join you in a live session to address those questions. And I will only address questions from the persons who have already submitted the tutorial. All right?
Okay, sir.
All right. Yes.
I sent you a message on Schoology in regards to hello?
Yeah, man, I'm listening.
In regards to the expansion of power system slots, sir, because they're only 20, capacity is only 20.
And it should be 40 because both groups have been placed in the same time slot. So it should be 40. I know the numbers that have registered for the module is a little more than that. So I have written to them and asked them to remove the caps on the class.
Okay, thank you,
Remove
sir.
the cap on the
Appreciate
class.
you. Yes,
All right? Yes, okay. All right. Have a good afternoon. I have to take the register next time.
Yes, sir. Thank you.
All right, good.